Yes. Hello, everyone. Nice to meet you, everyone. I'm Yulu from Japan, and I have been developing an open source library for Lean to perform Regex operations. And I present some experience verifying the implementation is correct with respect to the semantics. So let me start a bit about self-introduction. So I'm Yulu Pan from Japan. I use the Pandaman as the handle name in Zurich, so you can find me as Pandaman. I usually work as an engineer in some company, so my day job is about writing Java. Unfortunately, it's not Lean yet. I studied Lean around 2002-2003, and my main interest in software verification. Probably you might know me as the author of the Lean Regex, the Regex implementation in Lean 4 that is formally verified. A fun fact is that I have some Isabelle background, and two features I like from Isabelle is sledgehammer and functional induction. So I was very surprised to see functional induction came to Lean, and very thank you for bringing it to Lean. So let me talk about Lean Regex. So Lean Regex, the goal of the Lean Regex is providing a Regex implementation for Lean as a programming language. So it will provide many features that programmers expect when writing applications in Lean, such as substrate search, semantic character classes, and anchors. Maybe we can show some example here. I hope this is available in Zoom. But for example, we provide some small macros for compiling Regex expression in the elaboration time. You can find all appearance of this pattern in the haystack, given the positions. Well, we also support capture groups. So if you put parents in the regular expression, you can capture where exactly this expression matches in the haystack. So you get like AAA has these positions and BB has these positions. So this library provides this kind of like features that appear in many programming languages. And one of the main contributions of the library is that we give some formal operational semantics for these features and prove that the implementation is correct with respect to these semantics. We also care about the performance. So we provide linear time matching algorithm using the automaton called non-deterministic finite automaton. Also, we provide some optimizations to make it faster. And the good thing is that we can prove that it's correct. So we have some cool verified optimizations. So as I'm just a software engineer, and I'm only working this project in my spare time, so I'm pretty much looking for any new contributors. So that's the goal of this presentation. So next, let me talk about how we verify that this library is correct. So first, we talk about some scope of this verification project. So before like proving that implementation is correct, we must need to define what is the semantics of the regex in the first place. And this is actually a bit complicated because of the presence of some position-aware features in the real-world regexes. For example, anchors like hat and dara matches some position in the haystack without consuming any inputs. So if you put hat in the regex, it matches the beginning of the string, and dara means like the end of the string. So this kind of stuff requires us to track the positions in semantics. Also, capture groups record the position of the matches, and we need state to track that some matches in the semantics. And once we have this semantics, we can prove the correctness of the implementation. Here we prove the soundness and completeness, and I'll talk about what this means in later sections. Unfortunately, there are some gaps in the formalization. So we have some parsers and pre-processing steps in the library. They are regular Lean functions, so they are terminating, but we don't have proof for the correctness of these components. Actually, we have some bugs in the pre-processing step, so it's not like 100% correct, but I could claim that the primary part of the library is verified correct. Also, another interesting property of regex implementation is disambiguation. So for example, if you have a regex like foo or foo bar, some implementation just match foo even if you give the foo bar as the haystack. So this kind of policy selects one particular match among many possible possibilities, but this is not yet specified or verified because it's very tricky to handle it. So let me talk about let me next talk about how we specify the regex semantics in Lean Regex. So if you open the computer science textbooks, it usually talks about regular expressions and regular languages. So in the theoretical presentation, we have strings as a list of characters, and regular expression has a corresponding set called regular language, which is a set of strings that corresponds that matches a regular expression. And in theoretical account, we basically talks about the set membership problem. In other words, we check if the whole string matches. If we check if the whole string is in the set denoted by the regular language. But there are some differences in the real-world regex engine because usually programs work on some encoded byte strings instead of list of characters for performance, and we use some iterators so that we can track the some matches in the string. So there's some small differences in the string representation. Also, we provide the substring search function. So instead of checking if the whole string matches the regular expression, we find some parts of the string that matches the regular expression, which makes the semantics a little bit complicated. Also, as I talked before, we have some position-aware features, and we need to adapt the semantics to handle these features. So instead of using a regular language as a semantics, in this formalization, we use a kind of operation semantics for this regular expression semantics. So let me briefly talk about some formalities. So we have some syntax for the regular expression. The top one is the usual stuff like concatenation, unions, cluster, characters. But there are some additional stuff in the second line. The hat and dollar is anchors that checks the current position in the match, and this parenthesis captures the sub-match, and it records the position of this match E at the ice sub-match. So we give semantics like this: it prime pipe M. This means that regex matches the substring from position IT. This is an iterator to the IT prime. So we have this range of matches, and then it outputs the capture result as M. So here iterator is a position in the whole string. In Lean terms, we use we only consider a valid iterator. And also, as for M, you can regard it as a list of capture groups which records the position of sub-matches captured by these parentheses. So we have some select rules in operation semantics here. So if, for example, if you have this single character match, it matches only when the next character is C, and it proceeds the iterator by one character. And the union rule is usual. If you have this capture group, if the inner expression matches, it will also match and updates the capture group by adding a map from I to the positions of these matches. These two rules describes the semantics of the anchor. So it has some side conditions about current positions. And as for the concatenation, we run the regular expression independently, and it just concatenates the captured submatches. So with this formal semantics, I proved the correctness of the regex search functions in the lean regex. First, we proved that the match algorithm is sound and complete with respect to this semantics. Here, soundness is that if the match returns some m, m is actually a match as described in the semantics after the starting position. So one note here is that the matcher takes the starting position of the search. So please find this. Please start the search from this point. So it should find only the match after that point. And the inverse is the completeness. So if there is a match after the starting position of the search algorithm must return some result. It might not be the same one because it might find the earlier one, but it must find something. Actually, we proved the control position here. So if the search algorithm returns no, then it must indicate that there's no valid regex match after that position. So in the actual proof, the search algorithm, since the search algorithm operates on the string iterator, we need to take into account that the iterator might be pointing to like some position in the middle of UTF-8 by sequence. We excluded that possibility using the valid for from batteries. It allowed us to do some list-based reasoning for good iterators. So here's some strategy of the proof. We first show that so we need to talk about the comparison of regex. So we convert the regular expression into a non-deterministic finite automata, similarly to like how it's presented in the CS textbooks. And then we run such algorithms on that NFA. So we need to first show that the existence of match in the regex semantics and the existence of the path in the NFA must be equivalent. So this is mostly like textbook proofs. We need to adopt some small stuff, but it's not very difficult. But in some detail, we have some challenges in like organizing the proof, and I'm going to talk about that in a few moments. And once we have this equivalence, we prove that the NFA search function is sound and complete with respect to the existence of paths in the NFA. So this is basically like proving the correctness of graph traversal algorithms over NFA. So we have many invariants about the algorithm and prove that they hold. So that's basically the strategy of this formal verification. So next, I'm going to talk about some challenges I observed in proving the correctness. And one of the complications was about proving the theorems about the intermediate structure in the comparison step. So here's some diagram about like comparing the union expression. So we first start with like designated accept node in the NFA. We push the nodes for E1 to the at the end of the NFA, pointing that once E1 completes, it will transition to the accept node. Then we push the nodes to match against E2. Then finally, we push another node that makes the epsilon transition to the start node of E1 and E2, creating the whole NFA for E1 union E2. However, in this case, this NFA1 and NFA2 is basically like the local variable of the comparison function. So we don't have like this in the top level. So it was like, and when proving the properties about this comparison, we need theorems like that. You can when you have a path in this NFA1, you can lift that path to like a bigger one, or the converse. Like if you have a path in this NFA and it's on the left, it's within the bounds of the smaller one, that you can lift back to the smaller NFS. So these kind of properties are used in every proof, but it's kind of hard to state these theorems as a top-level theorem command. So I came across the Tulip thread about the proof data idiom from the Carlson project. What they did was like define a class about the input of some related part of theorems and state theorems, taking this proof data as an input. So I adapted the idiom for this case by creating a class for every regex variant in regex. So you have a structure like this. We have the inputs for the NFA comparison and inputs specific to this union expression. And then the theorems about these intermediate structures about the comparison can be stated as a theorem taking this class as an argument. So this helped reduce a lot of boilerplate in the proof by like introducing the classes in each proof. However, it introduced a lot more boilerplate. So at the end, it was better, but I'm not completely satisfactory. I'm also find that it's kind of hard to discover this kind of idioms when engineering proofs. So I wrote a blog post about this, but I think many of you have already found some tricks and tips you find useful when like formalizing theorems in Lean. So I would encourage you to like share that to the community. I would love to read that and make a comment. So the next challenge about proving the correctness of the algorithm is that the choice of the type for automaton state. So in Lean regex, the NFA automaton is represented as an array of nodes where each node has embedded transitions to the other nodes. And we identify each state by the indices to this nodes array. So the question is whether we should use NAT or FIN for indexing into this nodes array. It turns out that like using FIN is useful for like automatically discharging the like array index hypothesis, but when we are reasoning about the correctness of comparison, it involves like pushing states at the end of NFA, and it requires us to like reason about two NFAs with different sizes. So when I first used a FIN for proving theorems about it, it requires a lot of casts to like make indices compatible with different NFAs. So I ended up using NAT for this case. On the other hand, when we are proving the theorems about the NFA search function, it basically operates on a single NFA. So we didn't have this problem, and just using a FIN was much more convenient. So I ended up having like two definitions of paths in the NFA. One uses NAT and the other uses FIN. So we proved the equivalences at the end, but yeah, it was doable. And also, since Lean regex is intended to be used as a program or library in Lean applications, I care a lot about performance. So first things is that we use the linear time matching algorithm using the NFA simulation. So as you can see below, this is known to be a bad regex that cause exponential blow up in some engines. So note that the y-axis is log algorithmic. So you can see the lean implementation scales linearly or like log in this chart. But on the other hand, Python shows the exponential blow up. So it's good. Unfortunately, like it's tricky to prove the complexity stuff about the program written in Lean. So it's not formally verified, but we can see empirically. And one good thing about Lean is that Lean has native API for array. So you can just like constant time node access, and you can just push states, push stuff at the end of the array. So you can like do the same stuff in imperative language where you can push things about that. And that I really like that fact. Unfortunately, while the complexity sounds very good, the absolute performance is not, or like I would say they have some room for improvements. So if we compare Lean regex against the best in class regex engines in the world, it's like more than 3,000 times slower than the engines in, for example, Rust. But it's because that these engines use sophisticated data structures and algorithms such as DFS and SIMD searches. So I don't think like we have SIMD in Lean in the future, so in the near future. So I'm not going to match that. But even if we align the algorithm to use the same algorithm between Rust and Lean, it was like actually like 7 to 10 times slower, which was not satisfactory. Fortunately, we can use stock C profiler for Lean programs, and I took some profiling. It seems like that there are a lot of allocations and deallocations for small objects. So if you count the top 5 functions, you have like 48% of that time was spent on like allocations. So there are some room for improvement here. And also, we are working on implementing some verified optimizations in Lean regex. One of the famous technique in regex engines is to use prefilters so that if your regex engine is slow, you can make it faster by running it fewer times. So how you do that is that you extract some string literals and run faster string search algorithm first so that you can eliminate many possible starting positions. Very quick prefilter double speed in the base case. It was actually very easy to verify that correct. I also interested in integrating more sophisticated string search algorithm. We have KMP in batteries, but unfortunately we don't have proof about it. So maybe we need to look into that before integrating that. DFA comparison is also another technique that speeds up regex engine, but it's pretty tricky, so I'm not sure if we're going to do that. I'm also looking into ways to reduce allocations. So if you have any ideas that speed up the engine, please let me know. So we also have some contributors helping Lean regex get better. Thanks to Michael, we are extending prefilters to handle more cases. I'm also interested in generating Lean functions from regex that can use specialized information about the regex. I don't know if I have time. On the verification side, the disambiguation process is quite tricky to formalize and verify, so I'm interested to that. Another interesting aspect is the visualization contributed by Krishna. So thanks to proof widget and pen loss, like we can see the compiled regex, compiled NFA in the Lean widget, which is nice. So again, Lean regex is a regular expression engine I have been working on more than 1 year, and we have proof for the correctness in Lean, but the performance has some room for improvement. So we are pretty much looking for contributors. So if you are interested, please shoot me in Tulip. I'm Pandaman in Tulip, or like just talk to me today. Thank you.